So wood has actually many advances compared to normal metals and concrete and plastic and bricks compared to in construction, not compared, but in construction. These advances can be included that just the look and appeal from a look version. Not only do we have the appeal from how it looks nice and everything, but wood also can be lighter weight and stronger than a lot of these materials in certain aspects. So that is a huge advantage. It can also be easier to build with it, putting nails and stuff like that. Wood can actually be stronger than a lot of metals, pound for pound. Some wood, you can argue, is more CO2, emits less CO2 than metal, pound for pound. Sometimes you can argue it's more, or for some other ones, it depends on how far the different materials have to travel. It depends on how much you count destroying local environments, and everything with mining and stuff that destroys local environments. It depends also that you might see that metals are more recyclable. Metal technology is also evolving continuously, and always technologies evolve continuously. Another advantage of wood compared to like some other things is wood is a better insulator than many metals. Wood can also be bended in some ways, can handle sometimes bending better or is more rigid than some metals. So they can get some setting. It also can be made in come in more variety of shapes than bricks or something like that. So you can have the use there. But the things it's also more biodegradable if it goes in the environment, or more friendly to environment, less likely to leak in metals or other stuff that might be bad for the environment. So it's a mixed bag right there. It also, another advantage of wood that I think about it, is that you can grow wood, so you don't need to be near a local mine. So you could make it more local, and keep also carpeting and local knowledge more. However, wood has many disadvantages. It can really hurt the land locally. A lot of wood is not sustainably sourced. It's not the strongest material for the same volume. It also is not the most fireproof, obviously. It can rot and decay much more easily. So that's some big ones. And it does have a carbon footprint, certainly. So here I want to talk about some ideas that we might get the best of both worlds. And aesthetics is also very important, and I will say that because also aesthetics leads to mental health, better mental health for some people. One is we can do a carbonization or a similar process to make it more have a higher carbon content. And people have talked about this with like a Japanese wood making process, where they kind of burn it a little bit. You can also, people have done it with the first filaments for light bulbs, which is a carbonized cotton, where they took, and that whole process is to heat up in an atmosphere with very little oxygen or no oxygen at high temperatures, and a lot of the volatile stuff comes off, and that's with more carbon. This gives a burnt wood look, but instead it becomes less flammable until like 450 degrees Celsius or above. Now, its carbonization is not a. Now, how could we make this whole thing even better? Well, carbonization or a similar process better. And also to make it lighter weight and stronger, even then. And sometimes it depends later, sometimes worse, depends on the specifics. Well, how could we do it? Well, one way to really make it is to put it into a reducing atmosphere. So this is not an oxygen-free atmosphere. It's more than oxygen-free. This takes away oxygen actively by pumping in either hydrogen, H2, and H2 can has the benefits. They can really get into the smallest pores more easily, flow more easily through anything, but it also reacts more quickly. So you have the different kinetics. Yeah, we call the reaction speeds, how the reaction happens, kinetics, energy is different. Energy is like the end stuff. Looking at, we have the different, or you can throw in carbon monoxide, and carbon monoxide is more toxic, but it's more of a surface things and it interacts a little differently. It attacks different groups. The less hidden, the more the obvious stuff, surface one. So it'll give it a different burn. Or you put in organic things, gases such as methane, which has a carbon and hydrogen. Organic things we prefer have carbons and hydrogen in this process, and they remove some of the oxygen, and they can actually dump sometimes extra carbon in it. Now, this can, now with setting up with different mixtures of gases and adjusting temperatures, we can selectively make it more or less carbonized, or it's carbonized in different ways. So either it's more the surface, we can make it shrink faster, because when we do this, the whole thick process, there might be some shrinkage of water loss and stuff, but changing the shrink speeds can cause it, if you do really rapid cracks or something to add texture, or you can make the outside more dense as it shrinks on the inside that's still more the same, to give it a certain, make it like hollow and stronger, or you can change its insulating properties by changing the structure overall in the wood. So there's a lot of possibilities of playing around with this and turning the same wood into different types for specific uses. The other thing you can do, and that's all playing around with the gases, like I said, temperatures, to control the speed and how it gets carbonized, because different molecules carbonize at different temperatures. You might also have to adjust it for different types of wood and different, especially with the moisture content, which you can use sensors and everything for, to see how much different gases it's giving off, and heat sensors to also measure like the heating distribution. Maybe some some ones with liquid spectroscopy where you shine light or look at light to figure out chemical compositions. You can also gas sensors to look at the gas coming off. Another thing you could do to modify this process and more well control it is you can flow the gas in different ways. So you can flow it on top, so mostly interacts with the top layer. You can flow it at higher pressures, so it presses the whole thing more. Lower pressures where more stuff comes off quickly, but it also expands more. Different flow rates for also cause heating different. You can spray a local catalyst like iron oxide, which is widely available and cheap. And iron oxide speeds up carbonization locally and can also get trapped in the outside, and fused to the carbon and organic stuff in it to give it a certain structure that actually can reinforce and maybe make it even stronger. Or copper is another one, but copper metal more, and change the conductivity. Now, once you make these gases, you might be like, oh, we're making gases. These gases are reacting, making either water or carbon dioxide to some extent. And you're like, this is bad for the environment. Well, the thing is, to save energy, and this is the more efficient thing that I'm really proposing right here, is that these gases, then what we can do with them is use them to pump into an electrolysis cell at high temperature, and this electrolysis cell would then re-split it up. These electrolysis cells work significantly better at higher temperatures, so it requires less energy, and then you get the gases, feedstock gases back in there to pump it up, and you don't have to reheat it because the heat is trapped on the whole cycle, so you don't have to heat up these gases much. In fact, these gases bring in heat to this thing because the burning of the wood, not really burning, but the reaction of the wood heats up the gases, so it's less heating cost there. And now there is a problem with electrolysis cells. I'm basing it on the STEP process, which I'll add some links below, or the C2CNT process, where we use a molten carbonate electrolysis to split CO2 or hydrocarbons. But this does not work the best for water, because water does not dissolve the best in this chemical carbonates. So now that we have the point that water does not dissolve the best in these chemicals, we can send water into a different one pretty easily, because water is very easy to split off from other gases into a different cell where we have hydroxides, molten hydroxides, and molten hydroxides can split the water, and then the water can give off hydrogen, and that hydrogen is used again. Now, then you can have catalysts and stuff later on reacted to make fancier compounds of certain molecular weights and stuff like that. The splitting also, CO2 makes hydroxides not work as well because it reacts with the hydroxides, so it hurts that efficiency setup. So it's better to split it up, I would think. The reason why people discuss using molten carbonates and molten hydroxides is molten hydroxides have the formula of some, usually a metal on the periodic table, with OHs on it. This means then there's something called a Nernst equation in electrolysis. It says the more of the chemical you're splitting, the more efficient, the higher concentration, the more efficient it is. And when you have NO8s, what happens is it's actually the O8s kind of in the splitting water with NO8s. It's actually the O8s that's splitting up into oxygen and hydrogen. Then the Na or the sodium or whatever metal that makes the hydroxide is actually what's reacting with the water. So and then forms more hydroxide, which then splits again. So it acts like there's almost 100% water almost 100% water concentration you're splitting, but also being very, very conductive because it's molten. It's all these ions. When something's molten, ion electrolysis depends on the ionic conductivity. This is how much ions, which atoms with plus or minus charges, float around, how easy they float around. And molten high temperature stuff have it roll around some of the easiest because you can have such a high concentration. Like in water, you have some when you dissolve salt in it, but not all of it is in this form. If salt is molten, all of it's in this form. And also they move around more because it's a higher temperature, so all molecules are pumping around. Carbonates have a formula of some using metal, then CO3. And it's a CO3 part that's actually splitting, not a CO2, but it acts like this super concentrated CO2 there. Now, that can also, now once the gases are flown through it, we can pump out all the gases and store them, and then we can just let the whole thing cool down. But and then we can try to cool it down faster, slower, because that might cause it to have different types of cracking, and pump that heat into the system back if we take a more efficiently cold one, or with heat exchangers to really save a lot of energy. And this whole thing could also be run by renewable energy, so really free of it. So, and for the catalysts, if we use metal oxide catalysts in this whole process, like iron oxide on the surface something, that can also give it colors or different finishes. But those metal oxide catalysts are actually better for the environment than metal catalysts because you don't have to make the metal, because usually to metal oxides, two metals would consume CO2. Now you can skip that one. Or we can use metal ones, or we can use ceramic ones, and some ceramics exist in nature. Ceramics are complex inorganic things that usually do have some metal in them and oxygen. So that's the first very, very long part of this idea. Now, carbonized products will also have the advantage of only burning again at like 450 degrees Celsius or above, which is a lot lower than wood. It's more like 200 or something, you start getting wood. And the flames will spread slower, much slower. And also there'll be less energy in them to burn. So if they catch on fire, they won't heat up the surrounding place as much, spreading flames. And also they can potentially burn cleaner. Another idea along this line would be a supercritical soak or something similar. The problem with the carbonized thing I said before is without maybe sticking to the metal catalyst and really playing around with it, you do make something that's hydrophobic. And that's part of the reason why it doesn't water as much, because there's no water. But also because the reason why it doesn't, is because the molecule bonds are stronger, so it's harder for enzymes to eat it, and there's not as much sugar But a supercritical, and the catalyst also, if it stays stuck to the surface, we could also paint over it. But supercritical soak is, you take something like CO2, and there's also other organic compounds we've looked at of different various, some of them are called green because they're a lot less toxic and safer for humans. Some of them are not considered green, but in a controlled environment, they probably are pretty safe. CO2 is the safest, but it can take more energy than some of the other ones, and can be not the best one all the time for dissolving stuff. But anyway, supercritical is when you take something and you press it enough that's between either a liquid and a gas, or a liquid and a solid, or some other mixture of phases. And these things can soak through stuff better than normal usually fluids. It's like they have the properties of a liquid that help soak up, like in the towel, also of a gas that are not that viscous, or something like that weird. And they can dissolve into stuff that normally is hydrophobic or wouldn't dissolve liquids. This could be used to dissolve an implanted material with all useful chemicals to make it a better insulator, even more rot resistant, or to add functional groups to this thing. And the functional groups we add can do amazing things, such as, how would I say it? The functional groups can make something more easily stained or painted, which is the main thing that caramelization has in the past with firewood gone rid of, is the ability to paint and stain it or modify it with gloss. And these functional groups can make it sticky again to different types of paints and stuff, which can mean you can customize it more on site or even protect it more. You can also just make it heavier, more dense, which you might want for anchors or something like that, or just to add strength at the expense of weight locally. So it's stronger for the same amount, but it's also might not be as strong per weight. There's other soaks that people might want to look into it. If it's not too dense, you might be able to soak it with other chemicals by vibrating the whole thing. Now, a nice thing with some supercritical soaks is you can easily dry them up afterwards with just lowering the pressure, and then it just evaporates. And we collect it and recycle everything. Another kind of idea along this whole thing is to 3D print colors, or have a printer on it for printing colors and textures. Something that doesn't look like wood becomes looking like wood, and maybe this is actually metal or something. But then we can replace wood in a lot of applications with a more environmentally friendly version. We can also 3D print stuff print stuff over to make it more water resistant or something. Not perfect, but more. Now, the last idea I want to promote right over here is that maybe we can collect the waste cellulose from agriculture or something, and instead use that to make a lot of these fake woods or something. And we already have process to make fake wood and insulation of hemp, out of other fibers. And in the past, we have turned cellulose, the things that help make plants, into a bunch of artificial plastics. It actually was the first artificial plastic we ever wore. So it's a great idea that I think is really, really possible. However, this is not a guarantee thing. You have to also use more energy in some ways, because you have to press it together, and it's more like paper making. It could, but I think it would probably be a better insulator, because it could be made easily less dense. Probably also more fire resistant. So you might save some energy along the line. Well, thank you very much for listening. Please like and subscribe. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard. With your help, I think I can do it. Any ideas for future videos, comments, suggestions are welcome. Again, thank you very much. Goodbye.